Recording
Hello,
in
everyone.
progress.
Welcome to our lecture where we begin to talk about physical properties of solutions that are different from their pure solvents. These are what we call colligative properties. So we've been discussing at length the nature of solutes and solvents and how those come together to make solutions. We've talked about how we can use different concentration units to describe those solutions and how we can convert from one concentration unit to another. And now it's time to really take those concentration units and apply them to these physical properties of solutions that we're going to discuss in this next presentation. So let's jump into our conversation about colligative properties. So a colligative property, let's start with a definition. So a colligative property is a property of a solution that is affected, or I should probably say, is the direct result of a change being made to a pure solvent, where if we're talking about a solution, the change that's being made to that solvent is the addition of solute. So in a nutshell, a colligative property is any property of solution that is going to be different than the property of pure solvent. And more specifically, it's going to be a property that depends on the amount of solute added. So we're not really going to consider any kind of intermolecular forces, meaning like what the solute itself is, what the solvent itself is kind of no consequence. These colligative properties are properties that depend solely on like the number of particles of solute that are added. So I've said here amount matters. Any colligative property depends on your amount of solute, which we can express in terms of a concentration. And again, we're talking about this idea of like there not being intermolecular forces that we're going to consider. What does that really mean? So let's define something called an ideal solution. So an ideal solution is a really non-common way to think about solutions, right? You know, real solutions where we have interesting intermolecular forces, we've got some like thermodynamic properties at play. The volume of mixing might change as a result of our intermolecular forces, right? All those things that we know could potentially happen in our beaker when we add a solute to a solvent are going to be things that we like ignore when we're constructing this idea of an ideal solution. So when we're talking about colligative properties, we are assuming that we're looking at colligative properties in a solution that behaves ideally. So let's kind of go over some of the like nature or characteristics of an ideal solution or some assumptions that we make about solutions that allows us to treat them as ideal. So an ideal solution, this is a solution where the change in volume upon mixing is 0. It's also where the total entropy of mixing is 0. Sorry, enthalpy. So there's no change in any kind of thermodynamic property of our solution. And then also, this is where we have intermolecular forces that have to be present because otherwise we wouldn't be able to dissolve our solute and our solvent. But the total number and nature or strength is approximately equal to those in the original solvent. Meaning I can say that if I had solute IMFs in the pure solute sample, the total degree and strength and type of these intermolecular forces is equal to the solute solvent interactions in solution, which should be approximately equal to the amount of original solvent intermolecular forces. So this is in our pure solvent. So kind of like an ideal gas. In an ideal gas, we assume that there are like no intermolecular forces that are present. But in an ideal solution, we are assuming that the intermolecular forces that are present before and after solute is added are comparable to one another, right? So there's no like major change in the type or the strength of intermolecular forces present when you had just pure solvent versus when you have solute dissolved in that solvent. So we are going to focus on colligative properties of ideal solutions. And the first colligative property that we're going to discuss is one that is intrinsically related to this concept of an ideal solution. So this is the colligative property known as vapor pressure lowering. So we've seen this in our lab, our colligative properties lab, but let's talk about it. So Raoult's law, vapor pressure lowering in ideal solutions. So let's define one of our colligative properties of an ideal solution. So define Raoult's law. So Raoult's law says that the addition of a non-volatile solute to pure solvent affects a decrease in the vapor pressure recorded of the solution compared to the vapor pressure of pure solvents. Another way to say this is as the concentration of solute increases, the vapor pressure of solution decreases, or since we're thinking about how our solvent was affected by this addition of solute, we can think about this in terms of as the concentration of solvent in solution or the proportion of solvent in solution decreases, then the vapor pressure of the overall solution decreases from that of the original solvent. So I've got this diagram over here that we've drawn a couple times together, but I'll show it to you again. So we have a sample of pure solvent here on the left. So this is a substance that is in a closed system that has established a pressure equilibrium, a phase equilibrium between its liquid and gaseous phase. So we have some natural vaporization. And if we were to record on the barometer the total amount of pressure that's present due to all of these collisions between our vapor phase molecules with one another in the size of the container, et cetera, thinking back to kinetic molecular theory, this would read out our vapor pressure of the pure solvent, right? Just a sample of solvents. So if we were to figure out how much pressure the vapor version of the solvent particles are exerting, we call that the vapor pressure of the pure solvent. So what if we add now a non-volatile solute? So non-volatile solutes. These are things that have a negligible relative volatility compared to the solvent, meaning they don't vaporize very easily. So if I'm considering what's going on in solution that now has all of these yellow solute particles, these solute particles, again, kind of neglecting the intermolecular forces they're exerting on one another, and these solvent particles, right, assuming that kind of total intermolecular forces in this beaker is the same as in this, we see that just due to the presence of these kind of hindering molecules, there's like a physical blocking of all of our green solvent particles from statistically finding their way up to that boundary line between liquid and vapor and escaping into the vapor phase. So we have fewer vapor molecules of the solvent. So overall, if we were to read on the barometer the vapor pressure or the pressure that those lesser amount of molecules exerts in this system, we would see that the vapor pressure of the resulting solution, since it physically didn't allow our solvent particles to vaporize, this would be less than the vapor pressure of pure solvent. Now, the nice thing about an ideal solution is that this change that we see in vapor pressure as we continually add non-volatile solutes is one that is a directly proportional change. So I want to focus here, right? As the amount of solvent decreases, the vapor pressure of solution decreases. So if one variable trends in one way, and as a result, the other trends in the same way, this is a direct proportionality. And the concentration we are going to use in our discussion of vapor pressure lowering is the one that best suits the idea of mixtures of gases, which was our mole fraction. So we can write this by saying that the vapor pressure of our solution, the thing that is being changed, is going to be equal to the vapor pressure of pure solvent times the mole fraction, capital Chi, of solvent in solution. So as our relative fraction of solvent decreases. This means that our fraction of solute is increasing, meaning we have more physical blockages that are preventing our solvent particles from vaporizing. And so we then see a decrease in the vapor pressure of solution. So this is Raoult's law. Now, when we were talking about an ideal solution, right? We listed some characteristics of things that we assume about an ideal solution, things that are probably not super realistic, but in general, they're things that we are like kind of hand waving away a little bit. So there's a reverse perspective here that we can craft. So another way of saying or describing like an ideal solution, another way of saying this is what an ideal solution is ideal solutions obey Raoult's law. Because in order for this vapor pressure to be lowered in a directly proportional manner, we cannot have any change in the nature or strength of our intermolecular forces compared from like being our pure solvent to when we are now in solution. Otherwise, that would have a direct effect on how our particles are able to escape into the vapor phase, right? If I've got intermolecular forces that are repelling our solute and solvent particles, that might kind of push away our solution, or sorry, excuse me, our solvent particles out of solution a little bit more, right? So our vapor pressure might raise a little bit. So that'd be a positive deviation from Raoult's law. So just again, we're talking about an ideal solution, we're really saying this is something that can be modeled by Raoult's law, meaning we have this directly proportional change in vapor pressure of solution as our mole fraction of solvent in that solution decreases. So what does this look like? We generated a graph of this, right? Like we made something like this when we did our colligative properties lab. So let's look at kind of an experimental measure of a solution. So for example, if we have an ideal solution of component A, mixed with component B, let's take a look at what this little chart here is saying. So I'm going to start by looking at the, here we go, axis that is written that increases, right? Because normally when we read left to right on our Cartesian axis, we go from 0 to bigger and bigger numbers. So if I'm looking at the component that this particular axis is talking about here, highlighted in orange, that is solution component B. And we can see here that when we have no B in solution, our vapor pressure is low. And when we have all B in solution, the vapor pressure of B is high. So right here, when we are pure B, so mole fraction of B is equal to 1. This means we've got only component B. This is the vapor pressure of B pure. Let's compare that to the other component. So we've got A, and we need to kind of read this particular line backwards because our 0 and our 1 are reversed. So as we have all A in solution, meaning we've got a mole fraction of A equal to 1. This means we are purely A. And this point up here is the vapor pressure of pure A. So if I were to do kind of a quick little analysis, vapor pressure of pure A compared to the vapor pressure of pure B, right? This was where A was. We know that B is less volatile than A. So we would treat B, ideally, if it's like not super volatile, like its vapor pressure is pretty low in general, we would treat this like our solute in our Raoult's law model. Which means that A would be the solvent. So what are these lines showing? Like what are these green and orange lines showing? Let's look again at the one that reads in the direction we're used to reading them, right? So we are showing that as we increase the fraction of B in solution, so as we increase the amount of solutes, so if we increase the amount of solutes, then the amount of B that can make its way into the vapor phase is going to increase, right? We've got more stuff in the beaker. That is B. So then the partial pressure of B in the vapor phase is also going to increase. Now let's do this for A. So reading this, we're going to read backwards a little bit. There's my arrow, backwards. I guess we could read this one forward. Here, yeah. So here, looking at A, the more volatile substance, this would be our solvent, as we decrease the amount of A that is in solution, so the amount of solvent decreases. So as the amount of solvent decreases, then the vapor pressure of A that's found in the vapor mixture above our beaker is also going to decrease due to the presence of B blocking the way. And overall, if we look at what's going on with the solution, so this will be our line here in blue, the solution that is modeled by Raoult's law. This is saying that the total vapor pressure, so vapor pressure total, is equal to that of the vapor pressure of A and the vapor pressure of B in solution. And because we had a solvent that was more volatile than the added solute, we see that this line that connects our initial vapor pressures is one that overall trends downward. It decreases. So we see that we should have an overall vapor pressure lowering that we observe when we add more solutes or decrease the proportion of solvent. So this is Raoult's law. If that plot wasn't helpful to you, then think about this diagram here of what's actually going on in the beaker. Right, this is a little complicated. Let's get rid of some of these arrows. So the idea is non-volatile solute blocks the path of our volatile solvent, so fewer of our solvent particles make it to the vapor phase, thus the vapor pressure is lower. In our next video, we are going to practice the application of Raoult's law by looking at an example problem. So we'll see if we can figure out by how much the vapor pressure of solution was lowered compared to that of the pure solvent, given what we know about the components and concentration of those components in a particular solution. So see you then.